Expected value is perhaps the most useful probability concept that we're going to discuss. It has so many applications, from insurance policies and figuring out what an insurance company should charge to make sure they don't lose that much money, they're making a profit overall, to financial decisions, to casinos, playing some of all those games when you're gambling. There's expected value that's brought in there, and that's what casinos use to ensure that the different probabilities for winning are set in a way that overall they're going to end up making a profit. So as theoretical and experimental probabilities, a lot of the time, like in an experiment, let's say I flip a coin 10 times, I would expect to get ahead 50% of the time. But if I do an experiment on it, there's a possibility I'm only going to get 3 heads out of 10 tosses. So what the law of large numbers says is it says that the more and more we do an experimental probability, it'll eventually equal the theoretical probability. So the more that I do it, if I do hundreds of thousands of coin tosses and then I find the probability of that, the heads should get closer and closer to what that theoretical is of 50%. In person, I love to do this thing where I have each student toss the coin 10 times and they have a different probability for heads. But then when we put all of the tosses that they got, so we have like 100 tosses we're looking at, they see that the probability of getting a heads gets closer and closer to that 50% the more tosses that we make. So it's so similar to what I just said, but if you toss a coin 6 times, you can get ahead only 1 out of the 6 times. However, in the long run, after hundreds of thousands of tosses, the law of large numbers says that you will get ahead in approximately half of the tosses, 50% of the time. So the law of large numbers is used a ton when we're talking about lottery, because they're expecting hundreds of thousands of people to buy tickets, like policyholders for life insurance or automobile insurance. They'll have a bunch of policyholders. When it comes to casinos, they're expecting to have, over the life of having the roulette wheel, hundreds of thousands of people go through it. And so knowing that eventually the more people that go through, they'll get closer to that theoretical probability, they use that to find the expected value. So what the heck is expected value? So expected value is the mean value over the long run when the samples are repeated many times. So again, these policyholders, what they're going to do is they're going to figure out, and casino owners, what should I have as the payouts so that in the long run I end up making a profit as no matter how many people go, as more and more people go through here. So expected value is typically applied to events that have a cost and payouts that have been designed based on related probabilities. To calculate the expected value, what we do is we multiply each value and outcome by its probability and add up those products. So for example, for expected value, you find the value of event 1, so maybe it costs $1 to buy a lottery ticket, and then the probability times the probability of that. So probability of winning, so that would be 1 out of a million, plus the value of event 2 times the probability of that event happening. And you add all of those up for every event, and that ends up giving you that expected value. Let's actually use this. So let's look through this. So let's say we have a lottery ticket that has 5 possible prize amounts, and the chances of winning each are shown in this probability model below. So this is called a probability distribution table. I'm going to write that out. Probability distribution table. So the prize would be you'd win $1, and the probability that you'd win that $1 is 1/5. Prize of $10, the probability you'd win that is 1/50th. The prize of $50, the probability you'd win that is 1/100th. The prize of $1,000, the probability you'd win that is 1/2000. And then the prize of winning nothing, which would be $0, the probability of that is 1,539/2000. So if we wanted to find the expected value for this lottery ticket, the reason we use this probability distribution table is it makes it so easy to organize the information to figure out the expected value. So the expected value formula tells you do the value of event 1. So event 1 would be winning $1. So the value of that is $1. and the probability of that happening is 1/5. Then I add that to the next event, which would be the value of that is winning $10, and the probability that that will happen is 1 out of 50, plus the value of the next event, which is 50, and the probability that that will happen is 1 out of 100, plus the prize value of 1,000, and the probability of that happening is 1 over 2,000, plus the probability of $0 and the probability, plus the event of $0, and the probability of that is 1,539 over 2,000. So when I add all of that up, multiply and then add, I'm going to get $1.40. So what this means is that a player can expect to win $1.40 in the long run, like per ticket in the long run. So this gives that expected value for if, a player plays 1,000,000 tickets, they'll expect to win $1.40 per ticket is what it will average out to. So now let's look at one of the big things we need to think about is, well, how much does it cost to get a ticket? So here's what the lottery people will do. Well, and most casinos and all of that is they'll look at, okay, here's the prize amounts. Here's the probability of each prize amount to find that expected value. And then they make sure that the cost of the ticket is more than that expected value so that they're going to be making a profit over time. So the expected value, or what is going to be my net winnings, so my net winnings over time, if the cost of a ticket, so for those net winnings, so I'm expected to get $1.40 per ticket that I purchase, but it cost me $2 to purchase the ticket. So my net earnings are negative 60 cents. So after paying the cost of the ticket, the player can expect to lose 60 cents per game or per ticket in the long run. So this is how they get you, because you see this prize of 1,000 and think, oh, I could get that. But then again, the more times you play, the more people that play this thing, averages out that they're losing 60 cents per time they play. Overall, that's the average. Okay, so we kind of brought up that value, or that concept of net value. So the expected net value of a game, if it's negative, you're going to expect to lose money over the long run. So on that last example, you would lose 60 cents per ticket in the long run. That's what it would average out to. If the expected net value of a game is positive, you can expect to win money. And if the expected net value is 0, that's considered what is called a fair game, since neither the player nor the owner are expected to come out ahead over in the long run. Sadly, if you go to any casino or play the lottery, you're going to see in a lot of raffles, most, if not all of the time, the expected net value of the game is going to be negative to the player because these companies are wanting to profit in the long run. So for example, let's look at a roulette wheel. So a roulette wheel has 18 black numbers, 18 red numbers, and the numbers 0 and 00 in green. In roulette, betting on red is a 1-to-1 bet. That is, if you win, you gain the amount you bet. If you lose the money you bet. Suppose you make a $10 bet on red. What are your expected net winnings? So the first thing we need to do is figure out what is our expected value. So let's see, our outcome. So there's the outcome, there's the value, and then there's the probability. All right, so outcome of red, if it was red, I'm going to win $10. So that would, the probability of that happening is 18. So there's 18 reds to choose from out of 38 total possibilities. The other outcome would be it lands on not a red for me. I don't need to separate the outcomes of green or black because it's either going to be red and I win or not red and I lose. So I can lump those luckily all into the same category as an outcome. So if it's not red, I lose my 10 bucks. So the net that I would win if it's red is 10 bucks. The net that I would lose if it's not red is also 10 bucks. And the probability of that happening is 20 out of 38. So you can already kind of see what roulette is going to be geared towards, the player or the casino. It's definitely going to be the casino because your chances of losing 10 bucks is higher than your chances of winning. So if we had to find this expected net winnings, which is just the expected value, but in this case, I had what my net winnings would be. So my net winnings would be 10 bucks if I win, negative 10 bucks if I lose. So this expected value is going to be, okay, so I'd win $10. Probability of that happening is 18 out of 38. And then the value of I would lose 10 bucks. So I'd lose the 10 bucks I put up. And the probability of that happening is 20 out of 38. So when I put that in using technology, I'm going to get negative 53 cents. So this means we can expect to lose 53 cents. Oops. Per game over the long run. So obviously you're not going to lose 53 cents for this one game. You're going to either win 10 bucks or lose 10 bucks. But in the long run, if you average out all of your winnings and your losses, those will average out to 53 cents of a loss per game. All right, let's look at a lottery problem. So consider a lottery with 100 million tickets in which each ticket has a unique number. Each ticket is sold for $1 and is drawn for a single prize of $75 million, and there's no other prizes. Create a probability distribution for your net earnings from a single ticket X. Okay, so we'll call this event, which we'll just call the ticket. All right, the value of that event, and then the probability of that event. So I believe that there are just two events. Either you win or you lose. And I should have actually probably made these a little bit larger. Okay, so if I win, the value of winning is $75 million, except since I'm looking at my net, I have to take out what I did pay to play it. So $75 million minus $1 leaves me with $74,999,999. Okay, so again, when we're dealing with net, we have to take out what I've already paid. Well, if I don't win, I'm just going to be out my dollar, so it's negative $1. The probability that I win is, well, my one ticket would have to be chosen out of 100 million tickets. The probability that I lose is that one of those other tickets gets chosen. So how many of those other tickets are there? There's 99,999,999 out of 100 million. So now that we have this probability distribution, we could figure out the expected net value of a single ticket. So to figure out that expected value, all right, so it's going to take the value of 74,900,000, I mean, that's what we would hope we would get, right? 999,999 times the probability of that happening, which is 1 over 100 million, plus the expected value that we lose, so minus $1, and, or sorry, the event that we lose. So if we lose, the value of losing is you would be down $1, and the probability of that happening is 999,999,999 out of 100 million. So when I find this expected value by substituting this into a calculator, you will end up getting the expected value is negative $0.25, so 25 cents. So that means we can expect to lose 25 cents per ticket in the long run. Or in other words, the lottery is expected to earn 25 cents per ticket. Even with the payout, they will still earn 25 cents per ticket that's sold, which is a lot of money when you're talking about 100 million tickets. Okay, now let's look at this last example, which is a car insurance company. This is literally how these things happen. So Primo Insurance sells an annual car insurance policy for $1,350. Based on past data collected, on average, 1 in 50 policyholders will file a $6,000 claim. An average of 1 in 100 policyholders will file a $15,000 claim. And an average of 1 in 300 policyholders will file a $33,000 claim. Find the expected value to Primo Insurance per policy held. All right, so let's do our probability distribution table. So we have the event as one column, the value as another column, and then the probability. All right, so the event that they're going to have a $6,000 claim is, let's see. So actually, let's start out with the event that they have no claims. So the event that they have no claims. And I'm looking at the expected value to Primo Insurance. So I'm going to look at what will Primo Insurance make, not the policyholder. So that's something else that's important to consider when you're looking at these things and you're coming up with your values. Is it the policyholder, or is it the lottery ticket person, or is it the people that own the lottery or own the insurance company? And in this case, it's the insurance company. So if a person doesn't have any claim, well, the insurance company is going to make $1,350 on it. If in the event that a $6,000 claim is paid out, what's the value of that to the company? Well, the company has had, so the person that got the policy is paid $1,350, but now the insurance company is having to pay out $6,000. So $1,350 minus $6,000 leaves negative $4,650 is what the value of that would be, that policy to the insurance company. And that is 1 out of a 50 for the probability. The event that a $15,000 claim is paid out, well, the value of that, the policyholder's already paid $1,350, but now the insurance company has to pay $15,000. So the value of that happening to the insurance company, they will lose $13,650 on that policy. And the probability of that happening is 1 in 100. And then finally, that $33,000 claim. So again, that policyholder has already paid $1,350, but the insurance company is having to pay out $33,000. So in total, the insurance company will have paid out $31,650. So they'll lose that much money. So the value is negative. And the probability of that happening is 1 in 300. They didn't tell us the probability that no claims would happen, but I know all of these probabilities must add up to 1. So I've already taken care of 3. So if I figure out what's left here, so we're going to take 1 and we're going to subtract all of these other probabilities. So 1 minus 1 over 50, minus 1 over 100, and minus 1 over 300, which leaves me with 0.9667 for that probability. All right, now that I have this table, I can set up my expected value. So the expected value that no claim is paid out to the insurance company, they're going to make $1,350. The probability of that happening is 0.9667. It's a pretty good probability. Now, the value of the second event happening, a $6,000 claim to the insurance company, they would lose $46.50. And the probability of that happening is 1 out of 50. The event of $15,000, the value of the insurance company for that policy is negative $13,650. Probability of that happening is 1 over 100. And then the last event is paying out $33,000. The probability of that happening, so paying out $33,000, the value of that to the insurance company is $31,650. And the probability of that happening is 1 over 300. When I add that all up, I get $970.05. So what does that mean? Well, that means Primo will earn on average $970.05 per policy sold in the long run. So this is how insurance companies, they use someone that's called an actuary. It's a math job where they analyze risk. So what's the probability of, a $6,000 claim coming in? So they analyze that risk based on a bunch of factors and they'll figure out that probability. Once they figured all of that out, then they can go through and adjust, okay, how much should this insurance policy be? And that's why when you're younger, the insurance policies are usually higher than as you get older. Also, the more accidents you're in, you have more risk of getting into a car accident. So their probability of payouts is higher, and that's why your insurance policy is usually more than people who have not been in a car accident. So there you go. There's expected value for you.